Is this on? Oh, thanks. Okay, so this is a really cool seminar that we get to do between, so we're pairing the Ecology Spring Seminar Series. Our theme is Ecosystem Ecology with the Critical Zone Observatory Seminar today. So that's why we're at a new place and time, and why there's a very diverse group of people in the audience here. So Dr. Eissenstat is going to talk to us today about strategies of nutrient acquisition in temperate trees. Does anyone have any ecology announcements before he starts? Katie?
Still waiting for many of you in the ecology program to send me your articles and photos and the journal, the peer-reviewed papers or other papers that you've published in this last, since we had our last newsletter. So send them soon.
Also, there was a poll sent out to students in agricultural college about diversity. It's about the atmosphere and diversity. It's an opinion poll, so please be sure to fill that out if you've gotten it. And we also have a ongoing poll from the graduate school for input on the new ecology chair, the chair candidates that we have. There's two, and they have very different visions for the program. So make sure you check that out. It should be in your inbox from the graduate school. And we also have mini symposium coming up on November 29th, Wednesday. So keep that in your calendars for after spring break or Thanksgiving break.
you're talking about fungal species richness under different soil conditions or nutrient conditions, and you equated that with there not being a change in the community, but you can have the same number of species with completely different species between them, right?
I didn't show that's correct, and I didn't show all that data. So there was very little. So that also was not such an interesting story. There was the only thing that was interesting in all that work. This is not going to be good in terms of getting it published, but the thing that I was a little disappointed that there wasn't more things that were interesting. But the one thing that did come out is in the common garden, we found that ectomycorrhizal fungi, ectomycorrhizal trees tended to be colonized by ectomycorrhizal fungi that explored further away from the root, what we call long distance foragers. And that was interesting, but unfortunately we did not see it at Shale Hill. So it's one of these results that we're not sure how broadly uniform. But in general, it seems like there's a lot that goes on what fungal species colonize the roots that may not be directly related to function. It may be who got there first. It may be related to functional redundancy, and we don't have enough understanding of all the different functions of these fungi. There's probably a lot more there that we just don't have a handle on.
Get up too. So one of the things we're interested in at Shale Hills is the effect of tree throw. So when the trees fall over, I mean, you already know this, but when the trees fall over, they pick up all the soil and then it drops back down. So we end up with a pit and we end up with a mound. And then I've argued, that mound we've shown it's all stirred up. So now, given what you're talking about here, doesn't that mean that like really fast, or a lot of hyphae and roots would grow into that mound, or don't they grow up somehow? They only grow horizontal or something. I don't know. It's just a very open question. Would that mound really get colonized really quickly by roots and hyphae? And is there anything interesting there from what you know?
Good question. So the issue is when foraging on the order of 5 or 10 centimeters away, a lot of that can be done by fairly small amounts of growth by one root, and then it can proliferate by those first and second order roots. So in a tree throw, you may have to have roots grow 10 to 7 meters. And that requires the pioneer root having good communication with the tree to be able to grow out there and say, this is a real nutrient hotspot. And so these are the branches of the root system, the major branches. And we don't know, because we didn't study that, how responsible for a great big nutrient hotspot, if it is indeed a nutrient hotspot, how much the whole tree is going to reshift its root system. Now, everybody who's dealt with a sewer problem or root system know that trees can, if they find a nutrient hotspot, put a ton of roots where there's nutrients. And but we don't know, and that involves an entire shift in tree allocation around that zone. You might get that by a tree throw. That's a little bit different process because it requires the whole tree to be shifting allocation, not just to all sorts of roots, but pioneer roots and building shifting the shape of the roots. And what we know in canopies is that's not always the same. So we do know that fast growing trees may be able to shift their canopy pretty quick in an open canopy. So that may be more related to whole tree growth rate than related to thinking about morphology. Some of the forest people, would you agree with that? So that might be more of a whole tree growth rate response than simply the absorptive system.
So I would have expected thick-rooted species to forage with precision. I would have expected thick roots to forage with precision, and they with their mycorrhizae. So thick-rooted species to forage with precision through mycorrhizal, but they don't.
No. That was the initial hypothesis of Grimes' group. One of the ecologists that thought about foraging precision, he thought that. But it seems like what we're seeing is they're just not opportunistic. And there's a difference between the AM and the EM in this. In the EM species, the pines particularly were just putting out hyphae, whether it was organic patch or not. So that was why they weren't showing precision. They were into putting out a ton of hyphae. And it might be pine needles like to fall on the ground, they're recalcitrant. And we might find one of our hypotheses that pines really are territorial. And they really want to just occupy with massive amounts of hyphae that area where they're getting nutrients. But with the AM species, they just didn't grow. They were very slow growing. And so that was more because of no growth that there was no evidence of foraging. So the reasons were different between EM and AM, but the net result of not being opportunistic. So we didn't support in trees that original thinking by Grimes that slow growers or inconspicuous species might be more precise than the dominant.
This is okay now.
Any other questions? Well, thank you all for your attention. Got a little look of the hidden half, and there's still a lot more we'd like to discover. So those of you who want to hear more about topographical patterns are welcome to stay. This is kind of work in progress, a little less developed, but we'll talk about a recent student that worked at Shale Hills. And what we found out. I'll pause a minute, let people leave a few questions.
Did you say that EM fungi were evolutionarily more recent developments?
Yeah, there are more. They evolved more recently than the AM. Yeah, it's in there.
I didn't. Okay.
Went through my brain and put it out.
Oh, okay.
Yeah, yeah, it's under the PDF because that's a lot cleaner to read.
Okay. No. I guess I was asking, like, when was that? When did they evolve? Like, when in Earth's history did they evolve? Okay.
I don't remember the answer.
And neither do I.
Okay, I see that.
Yeah, that sort of stuff doesn't stick in my head. It's millions of years. That's all I remember. Yeah. Like, yeah, I don't remember.
Yeah, I was gonna say, when we say recent, are we talking, the Phanerozoic, past couple of million years? Like, what are we talking about?
No, I think like 60 million, something like that, versus when AM were around before when plants first colonized the soil. Okay, you guys can grab a seat if you'd like. So this is some of the work that I've been working with Lexi Orr on. She was a master student on the DOE project. And between her and Tom and a bunch of helpers, they did a lot of coring and analysis at Shale Hills. So everybody knows what the Shale Hills catchment looks like there in a different type of orientation. And so there's the ridge top, and we have swales and planar mid slopes, as well as valley floor. And we'll be looking at these slope positions and thinking about below ground. And so this was from Henry, showing the depth of soil, depth of bedrock, and how it tends to be, the deeper soils are in the valley floor and the swales. And this was the tree map that Margot and I put together And this was from Lauren's analysis of it. So she's the one who made the graphs looking at the tree size. And what you can see here is some of the biggest trees are in those swales and valley floor, and the smaller trees tend to be up on the ridge. And so some of this tree size seems to be related to hill slope position. So what we're going to focus on is partitioning. How much biomass gets partitioned below ground? And there's really two general theories. One is that it's optimal partitioning, that whatever resource is most limiting growth is where you're going to put your carbon. If light is limiting growth, you're going to put your carbon and get more light. If nutrients are limiting growth, whole plant growth, then you're going to put your effort into getting more nutrients. And similarly for water. So we might expect that more roots will be allocated to the ridge top and planar mid-slopes because of lower water content. But in a fixed or allometric partitioning, and a lot of people have kind of shown these global fixed allocation things, then it's basically saying it really doesn't matter, that it's pretty much fixed, that there's a fairly constant ratio of above to below ground carbon. There was a recent paper by Ferrier, who was here visiting, that kind of looked at a global data sets in terms of structural biomass as a fraction of NPP, and looked at fine roots as a fraction of NPP, net primary productivity, and they found that there was this real distinct pattern where roots were high, there tended to be less going into above ground growth, more into wood. I mean, less into wood, more into the roots. And here we're less into roots, a lot more into above ground growth. And interestingly, didn't see the same relationship for foliage. So what does this mean? This means that, or what they argue is, when you're in a forest and you're going after light, putting out additional leaves is not really going to help you. What you need is to get to the top of the canopy where you can get light. And then you're going to be in a better position to compete for light. But if nutrients are really limiting and light is less limiting whole plant growth, then you're going to put more of your effort into building roots. And so the trade-off in terms of allocation is between roots and stem height, not roots and leaves. And so this was relatively a recent change in thinking, because it used to be people were always talking about shoot-root ratios and mostly thinking about the shoot in terms of the leaf absorptive surfaces versus the roots. And that's really not where the trade-off is in forests. So we were interested if we were going to see some of the same patterns at Shale Hills, and we set up, and this is a lot with Jason and Tom. We set up all these different macro plots, and some were in swales, some were in valley floors, mid slopes, as well as ridge tops. And those of you at Shale Hills have seen all these different plots, and these are the 50 plots. And the plots were arranged such that there was a 5-meter distance between these, 1 meter distance, and this was 2, and this was 3 meter, to try to create spatial variation within the tubes for each of those blue macro plots that we call them. And this is where the soil cores were taken prior to the installation of the mini rhizotron tubes. And we broke down the cores into these depth increments. When we could get to this depth, often we only got to this depth, 60 centimeters or so. And they were taken in 2014, 250 cores. That was a lot of work. It varied where you were. But if we were in the valley floor, they could get down to 165 centimeters.
So you dug
or until the length of our core, which was 165 centimeters. So some of the soil might be deeper than 165 centimeters in some locations. There weren't many that went to the maximum depth of our core. The above ground measures involve leaf litter collection, LAI readings, the tree surveys that we already showed, as well as tree height. We used the LiDAR from Christian Brubaker's analysis. So what we've found is no surprise that the LAI tended to decline somewhat. Yeah, a little bit more open canopy at the ridge top than the valley floor. And it goes in that sort of pattern. And what each of these graphs shows is along that elevation gradient, we put the average along that elevation of where the valley floor is, the swales, the planar, and the ridge top as a bar to show what was the average of that slope position. And also these symbols, the circles are the ridge, mid-slope are the open circles, and the valley floor we didn't show on the swale. And this is the tree height, which is even a nicer response. Strongly significant. Slope position with tree height, where the trees are tallest at the valley floor, slightly taller at the swales than the planar, and by far shortest the ridge. I mean, this is a third shorter. This is a lot.
Is that top of the canopy or is that mean height?
That was the LiDAR return, the average for the macro plot.
Canopy top.
Yeah, canopy top. Right. So strong topographical effects on tree height.
So this is a stupid question. Tree height meaning from the surface. Like,
Right, from the surface. Yep, yep. So this is some of the things that Lexi collected. She did focus on just the absorptive roots, the first 3 orders of roots. And then also calculated the woody root biomass and length too. Did nitrogen by KCl extraction, organic matter loss, KCl extraction, rock content, and water content. This is a bit embarrassing data because Ted has much better data that would be nice to have for this, but we didn't have that at the time this was being put together. But Ted's been collecting a lot more data in the past year. So here is the rock content. So we do see some strong topographical effects below ground. Valley floor has much less rock content.
what does that mean? So this is like what is rock to you?
I mean, that's like asking a 2-year-old, what's a rock? Okay, no, I know. So the rock content, I think, was defined as greater than the sieve size of 2 millimeters.
Greater than 2
Yeah.
millimeters. In the entire core?
In that each one was sieved, each increment was sieved, and then this is over the whole core, right?
Right. So it's the rock content in the whole core. At
Right.
each site.
Right. And so this is and so depth of refusal is not included, obviously, in the core. But what we see is there's not much rock content, even though we were going much deeper with the valley floor. There's not much rock content. Grams per gram soil, is it? Gram. What? Yeah, per total, gram per total. Rock per.
Twice as much rock as soil, I guess is what you use. So it's greater than 2 millimeter over less than 2 millimeter. Is that right?
Yeah, that's I'd have to double check.
I think that's the only way the numbers make sense.
Yeah.
Oh, it's the greater than 2 millimeter over the less than 2
Right, it's not
millimeter.
a percentage. It's a-
Yeah, a ratio.
So the rock content is lowest at the valley.
Right.
Another way, yeah, or yeah, ton of soil.
And similarly, the soil depth. These are the average of the slope position. But you can see here, the soil depth really has a lot of spatial variation to it. You know, you hit some rocks, you just couldn't put the core in. So even though we have fairly nice average hill slope positions here, you know, these were the average of the macro plots, I believe. Or are these 1, 2, 3? Yeah, I think it's about 50 there. So I think those are macro averages. So even for a macro plot where you're doing 5, it's still really noisy. And this is going to basically underscore a lot of the problem we had. So inorganic nitrogen is not what we expected. We thought that the nitrogen might be higher in the valley floor of the swales, but we actually see higher nitrogen at the ridge top in terms of extractable inorganic nitrogen. This is combined.
In the entire core.
This I think is in only top 20 centimeters. But the volumetric water content, and I think these tend to be more distinct if you did season-long averages, right, Ted? But anyhow, the valley floor, as you might guess, has higher average soil moisture content at the time that was measured, and also a lot less noise than things like rock content. So one of the points here is that from a below ground resource limitation, it's not terribly clear. Nitrogen is going one direction, water is going the other direction. So if the trees are a lot smaller on the ridge, it probably is suggesting this is the driver, not this.
The water.
The water. And here's that impressive data we got for absorptive root length. So, but now think about it in the context of what we saw above ground. We saw all this variation above ground based on topography, and we're seeing within these standard ears. Now, the hill slope position, think about 5 cores per macro plot and maybe 10 or 15 macro plots for every slope position. So, you know, that's a lot of numbers being used to calculate the standard ear. So even though there's a lot of variability out there, these are pretty reasonable estimates. And they're not saying there's much of anything out there in terms of variation of root length density. And if you look at the individual points, they're pretty much all over the place. So if we try to look at something analogous to what I showed in the general idea from the literature, we're not seeing it. We're not seeing this nice pattern of less partitioning of roots in the valley floor and more partitioning of roots in the ridge. It's just not there.
Wait, so the way you just said that confuses me. Less partitioning in the valley floor, that would mean more carbon.
More is going into tree height. More is going into tree height. And less in the roots and the valley floor is what we hypothesized. And we're not seeing it.
Because they're trying to get up to the sun.
Right. We're seeing the strong effect on the way the trees grow above ground, but we're not seeing the trade-off below ground.
Well, isn't there something in here? I'm getting confused. I can't hold it all in my head, but you know, the soil is way deeper in the valley than it is in the.
No, but this is total. This is total length per unit ground area.
But I mean, just in general, I would think it'd be harder to be a big tree at the ridge because you got less soil to hold on to.
Yeah, that's a structural. But that would be more Yeah, so we didn't get into structural roots per se, but what's holding up the tree is mainly the structural roots, not these absorptive roots that we're talking about here. Remember, we're only talking about the first 3 orders of roots. They're very thin, very small roots. But the issue here is there's enormous variation, and there's no evidence that there is this kind of trade-off at the macroplot scale. So remember, and this is the sticky wicket, we're getting the average for a macroplot and the tree height for the macroplot. But what if the trees, they're not so confined in their canopy location by their light? If you look at a thing of trees, you see these nice canopy clouds. Each tree has its own little space, and it's fairly clearly defined. But the root system is not so confined by another species. While canopies overlap very little up there, the roots are overlapping all over the place. So the fact that this swale has what appears to be more abundance may not be because it may be that the trees in the planer or the leaves in the ridge are cheating. They're putting their roots out there in those hotspots. We already have showing that roots can be opportunistic. Maybe they're taking these nutrient hotspots and deeper soils of the swales to help support that tree, but we don't know because we can't assign here the roots of a ridge tree and just keep it to the ridge tree. So we're not able to assign specifically in this work, in this type of analysis, what belongs to a ridge tree. We can only say what's on this location. And so we may see an overabundance in some of these better zones that's not commensurate with the tree height at that zone. Did that make sense? So the allocation models we think about as an individual tree model. But when we're measuring roots in a forest, we don't know to what extent they're of the trees directly overhead.
There's something I don't understand about the premise, the relative partitioning premise, because it seems to me like as a tree grows taller, trees that are capturing more height also have to have more roots. But in this model, there's a trade-off, which leads to maybe an absurd endpoint where a tree is allocating all of its carbon to height and none to roots, which is impossible. To gain the height, they have to have more roots than their competitors that aren't gaining that.
Yeah, but the model does have a certain amount of nutrient requirements, so they have to have a certain amount of length. So these are actually more sophisticated models. These are these evolutionarily stable strategy models where they're looking at competition and competing for light versus competing for nutrients. So they do have to maintain some balance of needs. But it does suggest that where light is more being competed for, you're going to put more into tree height and less in the nutrients. But unless you're getting a certain amount of nutrients, you can't build tree height. What?
Is it observation or?
This is all observation, no model. The y-axis is, the same is true for the average. We thought maybe because there's so much variability, we'd be better using median. It didn't show any difference. But it's the total root length per unit ground area. So it's the average total root length of a macro plot, all the way to the depth we cored. So that's the median root length. And this is the height of the tree of that macro plot. What is the average height of the trees of that macro plot? So it's just looking at what is the relative effort into tree height in relation to the root length of that macro plot.
Do you think it's kind of a proxy for like the biomass?
Yeah, if we looked at total stem biomass, it would be very closely related to tree height.
So this is all roots, right? Not just fine roots.
These are just the absorptive roots. Right. You know, and the work that I showed you the picture, they were talking about, they also showed similar sorts of things for fine roots. But yeah, so this is just the absorptive roots. But we're thinking about it mechanistically. This is for below ground resource competition. This is for above ground resource competition.
The ability to discretize the depth with the
What?
roots, the root length per
Yeah, we could look at it at different depths, but it's just the stochasticity isn't going to make any difference.
Do you treat woody shrubs in that regard? Were they considered trees or were they ignored for above ground?
For above ground, they were overtopped. So it was the average height basically on the LiDAR. So they were not included on the return. It was the maximum height.
So that the roots showed up in the below ground.
They might have added some roots to the below ground. That's right. So one of the things I want to show you is this is the spatial variation of, she looked at 4 cores for root length density. And what you see here is while there could be a real hot spot, you know, of say 3 centimeters per cubic centimeter, this is of the 20 centimeter depth, and this is a root length density measurement. There also were often low spots in every single spot, and you're not, you know, and we could see these on the ridges as well as the valley floors. So this is really enormous spatial variation in this root length density that doesn't have a lot of structure, spatial structure in relation to topography.
Looks like most of the red is in the middle of the channel. Am I wrong?
These have a couple more red, that's true. But you know, you also have others that are showing a fair amount of red too. And any one of these also has some low spots.
Has that been mapped onto or correlated with the tree map? The species identification map?
We looked at, and in what context?
Well, the last time I recall looking at it, the species identified on the south ridge were different than what was located in the valley floor and again on the north ridge. But I'm just wondering, since we're looking at this variation in root length density strictly at the surface, if that has anything to do with any species or not.
I think it'll be hard with all the different species to pull that out. Let me finish here. So if you look at the coefficient of variation is an estimate of your standard deviation over an estimate of your mean. Now, if the estimate of your standard deviation is pretty cruddy, it's not such a good estimate of your coefficient of variation. But what we see here is often what you think with a lot of spatial structure is you'll have low variation when things are close. And as you get further away, you're going to have increased variation because things are more different. We actually, and this may be just a function of having much better estimates by so many more cores, we actually see that slope position is having differences between slope position is actually has a lower variation than you could have distance variation within a macro plot. Again, showing.
I don't understand this. So that's the coefficient of variation versus distance between the measurements.
Yeah. So
then there's something else plotted out there on the right.
Well, this is just different slope position. So the average of those means between the ridge, the valley floor, the mid slope.
So it's just plotted on the same plot. Even though
Well, it's off scale, but it's showing that this is further away. Okay, the hill slope positions are further away than 9 meters on average. But because there's not an exact distance, it's just to kind of get a frame of reference. But the point being that going here, you can have more variation in roots than going from the ridge to the valley floor.
there's more variation
That
small distances than.
That's right. So you can, there's a lot of fine scale variation when you're having cores that are only this big. And that's half the challenge of doing this sort of thing. But this is a standard size core, and so that's what people, it's tractable from a coring point of view, but it's not. In a place like Shale Hills, we're dealing with a lot of spatial variation. So in perspectives, tree species variation, root foraging could be one of the reasons we see roots varying like they do at these small spatial scales. They're putting roots into an area that's good and not putting roots in areas that are bad. And so that might be part of this fine scale variation. And that, of course, will be related to diameter and mycorrhizal type. One of the things, and it goes back to the question here, improved understanding will help if we could start identifying roots to trees. That will really add a lot if we know in a core the roots belong to which tree. Are we seeing ridge top trees really foraging much wider than trees in the swale or the valley floor? And that's why we're not seeing this nice connection. But because we're not connecting it to individual trees, these allocation models and trying to understand landscape patterns just don't hold. And we're not seeing, certainly at the landscape level, variation in roots in the same way we see above ground. And some of that may be just the difficulties of sampling. We're only getting a little glimpse of the patterns when we're, despite taking so many cores. So that's what we got.
So would it make sense to, or would it possibly make sense to put in those little root things, whatever you call those?
Ingrowth cores, yeah.
Into mounds and pits or something, and see if we get root growth into them, and how long it takes to get them in there?
I mean, we could, that question can be answered. I'm not sure it makes sense. It's all a lot of work, you know, in terms of, but people could certainly put an ingrowth core in there and see, you know, right now, the big problem is there's a lot of roots there. They may take a while to die, but you could put a fresh ingrowth core in there with no roots. And yeah, that would give you an idea of rates of colonization. That would be a way to get it.
Why would that not make sense? I mean, what piece of that seems nonsense?
Getting someone to do all the work. No, but if we could get someone to do it, that would be something we could do.
Well, putting the cups in doesn't take very long.
No, but it takes time to
Pull out,
yeah, count the roots. Yeah, but certainly that could be done. The thing is, you would want to probably do it all up because probably close to the soil you're going to see a fair amount. But how fast do they get to the upper part of the tree throw will be more of a question, more interesting.
We have to leave them there for a while, right?
Yeah, and that's always the question of how long should you leave them? Should we leave them for a season? Should we leave them for multiple years? But yeah, that would be a possible question that could be done. Yes, John, did you want? Okay.
Do we have an understanding of how far roots go? Like, if you're saying maybe ridge top trees can be going down in the swales. Like
You want records?
on meters?
Yes. So it wouldn't be uncommon for roots to be 20, 30 meters from the trunk.
20 or 30?
Yeah.
Just in a big tree, right?
Yeah. I'll ask any orchard grower who's got a forest nearby. Yeah, you can easily get trees going those kinds of distance. So they can go, especially something like the ridgetop trees, they can go quite a bit outside their canopy area to go after limiting resources.
That's not an absorptive tree.
No, that is a branch, but off the branch comes leaves. So anytime they got a woody root coming out there, they're going to probably be putting absorptive roots then to take up the resources. Give to John.
Yeah, so in contrast to what you're studying, when you have understory trees, they can put on very little height growth, very little diameter, but still have quite a few leaves because they're not getting much light, they're not fixing much carbon. They can remain viable 50, 100 years in that situation while they're waiting for an opening to occur in the canopy. The whole time they're building roots. So the roots are expanding further and further as the stem remains the same. They're putting their photosynthesis into the roots. These to be ready to bolt when the opportunity.
I don't know about the root side. They may be just hanging on. They may be just hanging on and maintaining a certain amount of root volume. I don't know how much the roots are actually increasing in that kind of.
Well, kind of, maybe this is forced the general kind of.
I'd like to see that study because it would require actually identifying the roots of that tree, of that understory tree, in a population of all these dominant trees, and that would.
Well, not all that difficult in a standard hardwood forest where you don't have that many stems per acre, and you have a finite number of small trees.
Seedlings.
Anyway, that's the general consensus. Is that, that's how one reason why trees, when they're released, by an opening mechanically, the shoots can grow so quickly because they have that great root absorptive surface available to them. So another way of looking at that is that the canopy trees you're studying are not limited at all in terms of light energy. They're maximizing their photosynthesis, and that allows them to have more or less equal above and below ground growth rates.
Well, yeah.
Or no?
Well, I'm not saying that what we found negates what those global data sets are saying, that there could be a potential trade-off. I just think at the scales we were looking, we don't see that trade-off. Because most of that is stand level data, of whole stands on different nutrient levels versus tree height, not variation within the forest. But I can see, and this was brought out, I think, with Tom's question too, that possibly these understory plants are contributing much more of a root signature to this variation, but we're not getting that signature, from the tree height side. And so some of this noise might be due to the understory root contributions too. So that might be partly what can be drawn from what you were saying.
So is what you guys are talking about, are you saying that the roots you looked at could be from understory trees?
Yes, I mean, we didn't expect them to be a major component, but they could be more significant.
So you not only can't tell one species from another when you look at a root, you can't tell whether it's an understory tree or a canopy.
No, we're just looking at the absorptive roots. That's right.
It seems to be a bigger omission is that, especially linking to the first part of your talk, is that we don't know about fungal biomass, right? So this foraging thing, bullet number 1 is right, and we would need to know the fungal biomass and the root biomass to know what the foraging is.
That's also true. Yeah, sorry.
I'm done now, though.
Yeah. Well, the point is that some of this water nutrient foraging might be hyphal based rather than root based, and that might also be a cause for why there's more variation. And that's also reasonable.
I think we're running out of time, but it surprised me. The leaf area in the stands surprised me. It was low. And like in the ridge tops, it's 3, which means there's lots of extra light being wasted in that forest. And in the valley floor, it's still just above 4, which is kind of like a midland level LAI forest. So what's going on? Why aren't these ridge tops wasting all that light? They're really that water or nutrient limited? I know you don't know the answer, but it struck me that it's a very low LAI.
Yeah. But on those ridges, it's pretty open. I mean, some of it's mortality too. Some of that, a lot of those trees are dying out there.
It could also be near that there's like trails there too, or the LAI measurements so low, depending on where those are.
Yeah, but the macropods are a little bit off from the trail, but still they could be picking up some of it.
Do you think there's an energy cost in developing nutrient sensing organs and fine roots of thin species versus tree species?
Nutrient sensing organs, is that what you're saying?
Yeah.
What's a nutrient sensing organ?
Well, like
Being opportunistic.
Yeah.
Okay, so is there a cost to being opportunistic? Energetic cost to being opportunistic? Most people feel there is. That having that kind of ability to be flexible might mean that you're keeping more more enzymes going. I mean, I don't know, John, have they looked at that at the more molecular level, plasticity? But I think generally we think of fast growers being more plastic. They have higher metabolic dark respiration rates. So I think they're at least correlated. I don't know. Yeah, that's one too, at least above ground. Roots tend to be indeterminate always, but above ground, certainly.
So the kind of anti-correlation between inorganic nitrate concentrations and root density, I think it was, seems to make sense, certainly with respect to, or soil moisture, sorry. The negative correlation between the trends in inorganic nitrate concentrations and soil moisture seems to make sense. One question.
Why does it make sense to you?
Well, I think if it's wetter, you're going to be losing more inorganic nitrogen.
Just from leaching
and other things.
Oh, denitrification
if
too.
You've got warm, oxygenated soils, you'd be able to nitrify things. So on that kind of surface level, that makes sense. What I'm curious about is how that might vary with depth, and then to what extent are different tree species able to use organic forms and uptake organic forms of nitrogen versus the inorganic forms.
Almost all of it was ammonium out there. Nitrate was pretty low, if I remember the data correctly. And all these trees can utilize ammonium pretty well. In terms of how it's distributed with depth, I just don't recall the data. We have the data, I think, or maybe we don't. Maybe Lexi only looked at the top 20. I don't know. Yeah. Yeah, sorry, we don't remember that. I have no more questions. I'm ready to call it a day. It's 1:30.